investigating the idea of inverses. If we have just a number, like let's say you have, let's say 5x equals 25, just with numbers. Typically, how would we solve this for x?
We make it 5y.
Sorry, what was that?
For inverse, is this when we would switch the x and y?
Oh, not inverse functions. Just how would you, if you just have 5 times x equals 25, how would you isolate x there?
Oh, I divide 5 by both sides.
Yeah, typically we just divide both sides by 5. What if we wanted to do that without division? Could you accomplish this with just multiplication instead?
Multiply by 1 over 5.
If we multiply both sides by 1 over 5, that'll work because what's 1/5 times 5?
1.
Right. Those cancel out to just 1 times x equals 1/5 times 25. And 1 times x is just x. So if 5 times x equals 25, we can find x as a value by multiplying the inverse of 5 times 25. So this would be the idea of a multiplicative inverse for numbers. 1/5 or 0.2 is the multiplicative inverse of 5. In the sense that when you multiply them together, you get 1, the identity element for multiplication. We can do the same idea with matrices. If you have a matrix equation of the form of something like, let's say you have some matrix A, let's say we know what matrix A is, and it's multiplied by some unknown vector x, and the result is a vector b. So let's say we know what vector b is, and we know what matrix A is. And we're trying to find vector x. We can't exactly divide by matrix A. There's no division operation defined for matrices. But just like we could get rid of the times 5 by multiplying by the inverse of 5, we can do the same idea here. If we multiply by the inverse of matrix A, and order matters for matrices. So if we're multiplying on the left side by the inverse of A, we also have to multiply on the left side by the inverse of A. So left multiplying by A inverse and also left multiplying by A inverse, since order matters. In that case, the whole point of this is just like 5 inverse times 5 equal just the number 1. What would you expect to happen if we multiply A inverse times A for any meaningful definition of the word inverse?
Always is also 1.
It would be 1 if they were numbers. But if these are matrices, like let's say A is a 3x3 matrix, A inverse is also going to be a 3x3 matrix. So when we multiply, we're going to get another 3x3 matrix. So instead of the number 1, we're going to get a matrix that acts like the number 1, which is also known as what?
Identity.
Yeah, the identity matrix. An inverse of a matrix is a matrix you can multiply by that matrix to turn it into the identity matrix. Just like the inverse of 5 was a number you could multiply by 5 to turn it into the number 1. So any matrix times its own inverse, by definition of inverse, is going to be the identity matrix of the appropriate size. In this case, 3x3. That's still multiplied by this number x, or this vector x. And then on the other side, we've got A inverse, whatever that happens to be, times vector b. But what's the identity matrix times vector x? What happens to any matrix or vector if you just multiply by an identity matrix?
B itself.
It's just itself, yeah. The identity matrix doesn't change it. Just like multiplying a number by 1 doesn't change the number. The identity element, the identity matrix acts like the number 1, but for matrices. X multiplied by the identity matrix is just X itself. So this provides us with a way to solve a matrix equation. If you've got a matrix equation of the form a known matrix times an unknown vector equals a known vector, if you have some way of finding the inverse of that coefficient matrix, you can left multiply both sides by A inverse. A inverse times A cancels out to the identity matrix, which just leaves you with X equals A inverse times B. And since any system of linear equations can be written as a matrix equation, then this provides us with what can sometimes be a very rapid and systematic way of solving any system of linear equations. Any questions on that so far? Then let's try out an example. Let's say we have put together a system of equations here. So here's a system of equations. The idea is we can write this system of equations as one equation with matrices. If we think of our unknown variables, x, y, z, as a whole vector. If we take that x, y, z vector and multiply it on the left side by a matrix, let's say you take the first row and multiply it by this vector. So something x plus something y plus something z. But what are some coefficients of x, y, and z that would be relevant here?
For the first row, it's 1, 4, and -3.
Yeah, if I just fill in the coefficients from that first equation, 1x, 4y, minus 3z, 1, 4, -3. If we were to multiply this, we'd get 1x plus 4y minus 3z. And what do we know about 1x plus 4y minus 3z?
It equals -13.
Right. So instead of writing equals x plus 4y minus 3z, I'm just going to substitute -13. And likewise, if we take the coefficients from the second equation, 6, 6, -3, combining this row and this column will be 6x plus 6y minus 3z, which we know has to equal what? Yeah, that's got to equal 6 from this second equation. And likewise, the third equation, 5, 1, 1, by standard matrix multiplication, that's going to be 5x plus 1y plus 1z equals the number in that spot, which then has to be 2. So this system of 3 equations, 3 unknowns can be written as one equation with a 3x3 matrix, a 3x3 unknown vector, and another 3x1 vector of numbers we know. Or to abbreviate that, matrix A, the coefficient matrix, times vector x, the vector of all 3 of the unknowns, equals vector B. So this is a very convenient way of writing a system of equations as just one equation. And if we can find an inverse for matrix A, then we can just left multiply both sides by matrix A inverse. A inverse times A becomes the identity matrix, which leaves us with just X equals A inverse times B. So if we can find an inverse for matrix A, then we can just multiply that inverse matrix times -13, 6, 2, and we'll immediately have the solution for X, Y, and Z. So this is one of, not the only, but one of many applications of an inverse matrix. You can use it to very quickly solve an entire system of equations all in one step. Any questions on that so far? So let's see how we might actually find that inverse matrix. Let me put this off to the side. And we'll come back to these values later. But if we wanted to find the inverse of A, first of all, to even be invertible in the first place, by definition, we want A times A inverse to equal the identity matrix. And we also want that to work in reverse. This is one of the rare instances where matrix multiplication is commutative. We want A times that same inverse matrix to also equal the identity matrix. So if we look at this in terms of dimensions, let's say A has dimensions m by n. In that case, what would the dimensions of A inverse have to be? Yeah, or at least something by m, because these inner dimensions have to match up. And likewise, if A is still m by n, A inverse has to be n by something to get those to match up. So this would also have to be n by n as well. However, it turns out we can only really guarantee this under certain circumstances, that many matrices do not have inverses at all. And one of the restrictions is that A has to be a square matrix. If A is not a square matrix, there isn't really a reliable way to invert it. So we're going to assume A is a square matrix. So let's say n by n, same width and height. And in order to invert that, based on the property we want it to have, if you think of this in terms of linear transforms, like if you have matrix A and you multiply by some input vector X, and the result is some output vector Y. If you multiply both sides by A inverse, then what's left? What would this entire side of the equation become? Yeah, we're left with just the X vector. And then over here, we've now got A inverse times Y. So in this sense, it does act a little bit like a inverse of a function. If you think of A as an operation being done to this input to get an output, the inverse matrix takes the original output and gets you back to the original input. So the inverse of a matrix undoes whatever the matrix does. For example, if you have a matrix that has the effect of taking a vector and rotating it 40 degrees clockwise, the inverse matrix will take the vector and rotate it 40 degrees counterclockwise. It does the exact opposite of what A does if you think of it in terms of a transformation applied to a vector. Any questions on the meaning of that so far? So if we want to actually calculate that that matrix, to find A inverse, we usually do this with augmented matrices, because we know that if we have some matrix A, and let's say we multiply it by A inverse, that should have the effect of completely canceling it out, leaving us with just the identity matrix. And we can use row reduction to find this, because if we set up an augmented matrix of matrix A, and in this case, we're going to augment that with not just a single column, but with an entire matrix, specifically the identity matrix. And then we do row reduction. Because ideally, row reduction, we're trying to get this into reduced row echelon form. What's the simplest this square matrix could become if row reduction works perfectly? What's typically our goal in row reduction? Like if we were using this to solve, if we had an augmented matrix we were using to solve a system of equations, if you want to get an actual specific value for X, for the input vector, X, Y, Z, what should you want this to row reduce all the way to?
One or zero?
Well, this is an entire matrix though. So specifically, where would the ones and zeros go if we get an actual specific solution?
We want like we want the identity matrix.
Yeah, if this turns into the identity matrix, then whatever's left here will be the solution. Ultimately, the reason why that works is each one of those row reduction steps is a transformation. If you think back to what we were doing last time with the transformation matrices, like each row operation, adding a row to another row or subtracting a multiple of a row from a row, all those can be represented as transformation matrices. So as you're row reducing, you're applying some transformation to matrix A, but also doing the same operation to vector B. So if you look at this in terms of row operations, each one of those row operations can be written as some elementary transform matrix. Let's say E1. If E1 represents the first step you do, maybe like add 3 times row 1 to row 2, you're doing that to both A and B. And then maybe you do another operation, E2, to both whatever you have so far here and whatever you have so far here. And then another operation. And eventually you get to a point where maybe what's left here is the identity matrix, which means X equals B modified by whatever steps you took to cancel out A. We're ultimately doing the same thing here. We're doing some row operations, not only to a row of A, but also to the corresponding row of the identity matrix. Those row operations, ideally, we want to cancel out A entirely to get to just the identity matrix. And whatever's left on the other side, because all these row operations represent some sort of transformation matrix applied to A and applied to the identity matrix. So if we take A and the identity matrix, apply the same elementary transformations to each one, and let's say after applying certain steps to A ends up canceling out completely to just the identity matrix. If we've got a bunch of stuff multiplied by A and we get the identity matrix, what's the bunch of stuff we multiplied by? What multiplier would turn A into the identity matrix by definition? Yeah, that's going to be the inverse. So if we can find a bunch of operations that turn A into the inverse or into the identity matrix, those operations that we did together are the inverse of A. And if we do those same operations to the identity matrix on the other side of the augment bar, then the other side of the matrix is going to become A inverse times the identity matrix, which is just A inverse. So this is the core idea of how to find the inverse of a matrix, or at least one method of finding an inverse. You take the matrix you have, which has to be a square matrix, augment with the entire identity matrix of the same size. Row reduce, if you can row reduce the left side all the way to the identity matrix, the steps you're doing are the steps that invert A. So applying those same steps to the identity matrix will result in A inverse. Because what we're doing here to identity matrix represents all the steps that it takes to undo matrix A. Any questions on the theory behind that so far? And again, in terms of the actual calculations, to find A inverse, augment A with the identity matrix of the same size, row reduce all the way until A turns into the identity matrix, and the right side, whatever's left, will be A inverse. With one exception, what happens if A cannot be row reduced to the identity matrix? For example, maybe you get a row of all zeros. What would that suggest?
No inverse.
Right, some matrices don't have inverses. Even if it's a square matrix, it's possible that A cannot possibly be row reduced to the identity matrix, typically because one of the rows has no pivot, it's just all zeros. That would tell you that that matrix does not have an inverse. Typically in those cases, we call that matrix singular. The term singular means the matrix has no inverse. It also means a bunch of other stuff as well, because any matrix that is square but does not have an inverse automatically has a long list of properties that it must have as well. Or a non-singular matrix, a matrix that does have an inverse, also has a bunch of other properties it must have. So any square matrix can be split into one of two categories: singular matrices, which do not have inverses, and non-singular matrices, which do have inverses, and a bunch of other properties as well. And over the course of the quarter, we're going to look into some of the other properties. Like if you know this thing is true, then that means the matrix must be invertible, and you know a bunch of other stuff about it as well. Or if this thing is false, you know the matrix is not invertible, and you immediately know a lot of other stuff too. So they're very useful ways of categorizing matrices and quickly learning lots of information about that matrix. But let's try this applied to that matrix we were looking at earlier. Let's see if we can actually find that inverse. Starting with that matrix. So this is matrix A. We're going to augment that with the 3x3 identity matrix. And we want to use row operations to get this all the way to reduced row echelon format, ideally all the way to the identity matrix. So what would be a good first step? What's a row operation we can do that will get us on the road towards row reduced echelon format?
Multiply row 1 by -6 and add it to row 2.
Yeah, because that'll help us use this pivot to eliminate something in the same column. So modifying row 2 by adding -6 times row 1. And in the same step, we may as well also cancel out this 5 by adding what to row 3. Yeah, if we add -5 times row 1, that'll cancel out the 5 there. So let's see what we get. First row, we're not changing yet. So that's just 1, 4, -3, 1, 0, 0. Second row, we've got 6 minus 6, 6 minus 6 times 4. So 6 minus 24 is -18. -3 minus 6 times -3 would be -3 plus 18. So that'll be 15. 0 plus -6. 1 plus nothing. 0 plus nothing. So that's our new second row. And then third row, 5 plus -5 cancels out. 1 minus 20. 1 plus 15. 0 minus 5. Nothing plus nothing. And 1 plus nothing. So that's our new second and third rows. Any questions on that so far? So as our next step, this 1 is now alone in its column. What's our next pivot? Yeah, the first non-zero in that second row is this -18. So we're going to want to use that -18 to eliminate the numbers above and below. And the default step, if we didn't want to mess around with the procedure, if we just wanted to follow it exactly step by step, would be to divide that whole row by -18 so we get a 1 here, then use that 1 to eliminate everything above and below. The only problem with that is, since these are not all multiples of 18, this is going to lead to some somewhat messy fractions. It'll still work, it just might be a little tedious. Do you want to try that, following the procedure step by step, or look for an alternate method that might make the numbers a little easier to work with?
Can we try making the number easier to work with?
Yeah, let's try that. If I were just setting up a computer program to do that, then I would just say, yeah, divide that by -18, you can handle it at your computer. But since we're not computers, it might make sense to break out of the instructions a little bit. Do you see any other way to combine these numbers or multiply or divide by something that might make a new number that's easier to work with? Ideally, what do we want that number to be?
We want it to be a 1.
Yeah, we want a 1 here. By the book, we would accomplish this by dividing this row by -18. But do you see any other way we could use the other numbers we've got here to turn this into a 1 more easily, without resorting to dividing by something that's not a factor of everything in the row?
Would it make sense to like multiply it by 4 first?
One way to do it would be to multiply this by 4, and then also multiply this whole row by 18. That way, these would be the same nice, neat whole number.
Mm-hmm.
So that's certainly one way you could do it. You could multiply this whole row by 18 and this whole row by 4. So these are the same nice, neat whole number. But then if we wanted to apply that to this one and this one, we'd have to multiply this row by 19 and this row by 18. So these match up because they've got no common factors. Mm-hmm. So I think that it would certainly work, but it would lead to some very, very large numbers, which would make things, I think, possibly even more tedious than dealing with the fractions. Divide by -3. We could certainly divide this by -3 because these are all multiples of 3 except for the 1. So that might make things a little easier. But I'm also thinking we can add any rows together we want, right? I'm noticing that -18 and -19, we can use those to make a 1 very easily by doing one operation, without even needing any fancy multiplication or division at all.
Add it?
Yeah, if we just add or subtract those, yeah, R2 minus R3. And again, this is not a strict by the book, follow the instructions step-by-step sort of thing. But by breaking out of that a little bit, but still using a legal operation, adding a row to another row or subtracting a row from another row, I'm thinking this could get us a 1 much more easily. So let's break out of the usual step-by-step procedure and try this and see what happens. First row, we're not changing at this time. And ideally, if we're doing it right, any procedure, as long as we're following the row operations that are permitted, once we get to reduced row echelon format, it won't matter what procedure we took to get there. All those paths should lead to the same final reduced row echelon format. So let's try this. Subtracting row 3 from row 2. 0 minus 0. Negative 18 minus 19 is negative 18 plus 19, so we get 1. 15 minus 16 is negative 1. These numbers are looking easier already. Negative 6 minus 5 is negative 1. 1 minus 0. 0 minus 1. This row looks like it's going to be a lot easier to work with. Any questions on that so far? And then third row we'll keep as it is. And at this point, we now have a 1 in the pivot space. This pivot is a 1 and alone in its column. This pivot is a 1. It's not alone in its column yet. So what do we need to do to fix that? How could we get rid of this 4 here?
Multiply row 2 by negative 4 and add it to row 1.
Yeah. And that's now going to be much easier to deal with because the pivot was made into a 1. It would still work with the negative 18. It would just lead to the numbers being much more annoying to do by hand. And while we're at it, how would we get rid of this negative 19?
Multiply row 2 by 19.
Yeah, 19 times row 2. We'll use that 1 to cancel out that negative 19. So let's see what that looks like. That should get us to the second column cleared. So first row, we got 1, which doesn't change because we're just adding 0. 4 plus negative 4. Negative 3 plus 4 becomes 1. And then carrying that through the rest of the row with the modified identity matrix. 1 plus 4. 0 minus 4. 0 minus 4. So I'm getting 5, negative 4, 4. And then second row, we're not changing. And third row, we're adding 19 times the second row. So 0 plus 0, negative 19 plus 19, 16 plus negative 19 should be negative 3. Negative 5 plus negative 19 is negative 24. 0 plus 19. And 1 plus negative 19. Any questions on that so far? So checking where we're at, this pivot is a 1 and alone in its column. This next pivot is also a 1 and also alone in its column. Our next pivot is not a 1 and not alone in its column. So we're going to need to modify this to a positive 1 and also eliminate everything above. We could do that in either order. But since I don't see any easy whole number multiples of negative 3 that will cancel out a 1 or a negative 1, we're going to have to mess with fractions anyway, no matter what we do at this point. So we may as well just cancel out this negative 3 by multiplying that whole row by negative 1/3. So let's do that as the next step. It looks like some fractions are going to be inevitable here, but we can at least save those for the end. So first and second rows, we're not currently changing. But the third row, we're multiplying by negative 1/3. The zeros stay as they are. Negative 3 times negative 1/3 is 1. Then we get negative cancels out. 1/3 of 24 would be 8. Negative 19/3, I'm just going to leave as a mixed improper fraction. 18 over 3 is going to be 6. So we at least only have possible messy fractions in this column. And there's not really any way around that. Sometimes inverses of whole number matrices do have fractions in them, oh well. And at this point, we now have this pivot as a 1. How do we eliminate everything in the same column? What are our last couple of operations we're going to need to do here?
We add row 3 to row 2.
Yeah. Because that way this 1 cancels out this -1. We also want to get rid of this 1 on the top one. So what else do we need to do?
Add negative row 3.
Yeah, if we just add negative row 3, or we could even just write that as subtract row 3. That should do it. So let's see what that turns into. And this should be our final step in finding the inverse matrix. So subtracting row 3 from row 1, 1 minus 0, 0 minus 0, 1 minus 1 cancels out. That's the row of the identity matrix we want. And then carrying that through the rest of the row, 5 minus 8, -4 minus 19 thirds. So -4 plus 19 thirds. We'll want to write that as a common denominator. So what's 4 in thirds?
12.
Yeah, 12 thirds. So -12 plus 19 would be 7 thirds. So that's this middle number here, positive 7 thirds. And then 4 minus 6. So that's our first row. Second row, we're adding row 3. So 0 plus 0, 1 plus 0, -1 plus 1. Continuing the rest of the row, -1 plus 8, 1 plus -19 thirds. So that's 3 thirds minus 19 thirds should be -16 thirds. -1 plus 6 would be 5. And then third row, we just keep as it is. So the left side is now the identity matrix. We're done with the row reduction, which means the right side has to be what?
Inverse.
Yeah, that is an inverse. This matrix is the inverse of the original matrix A. Any questions on that procedure?
I had a question. So on like the left side of the board on the bottom, you know how we multiplied it by 1/3?
Yeah.
Could we have like it? Would it be wrong? Oh well, no. I guess I understand it now. Because if we multiplied row 2 by 3 and added it to row 3, then the 0 would turn back into another number, right?
Right. We don't want to use this 1 to change the 0 we've already made. That would be undoing the progress we've already made. It would certainly be a permitted row operation. It just wouldn't be a very useful one in that context.
Yeah, that makes sense.
One other way you could proceed, instead of taking this row and dividing it by -3, you could multiply the first row and the second row by 3. So now everything is multiples of 3. But then at the end, you would have to divide everything by 3 anyway. So it is certainly an option if you want to hold off on the fractions until the very last step and work with whole numbers the whole way. That is certainly a possibility. But I was just thinking at this step, we've only got a couple more frames to go anyway, so we may as well just get into the fractions at this point. Also, now that we have allegedly the inverse of A, how could we check to make sure it really is? How could we verify, yes, this really is the inverse of matrix A? What's the one ultimate test that tells us, yes, these really are inverses?
You can multiply the inverse by A.
Yeah, if we multiply the thing we think is A inverse times the original matrix A, what should we get if we've done everything right?
The identity matrix.
Right. So this is one of the nice things about finding the inverse of a matrix. If you're not sure, you can always check your answer by multiplying it by the original matrix in either order. They should both give you the same result. They should both give you the identity matrix. And also, now that we've got the inverse, we can solve that original system of equations. If we multiply the inverse of A times B, the original vector from the other side of the equation, then whatever's left should be X, the original X, Y, Z unknown vector. So once you have the inverse, solving the system of equations is really fast. You just multiply A inverse times the B vector, and the result is the X vector. The only problem, of course, is that finding the inverse matrix can be really tedious, as you see from this entire marker board. In fact, we find the inverse matrix by augmenting and row reducing, which you'd have to do if you're just solving it by augmenting and row reducing in the first place. So if you're just solving a system of equations, this method doesn't really save much time. But it does have two big advantages. First of all, most graphing calculators and a lot of computer utilities that use matrices can quickly do an inverse matrix just by typing in the original matrix and saying, find the inverse of this. So if you have access to a graphing calculator or a computer and you want to solve a system of equations really fast, what I usually do is just type in the matrix coefficients and say, this inverse times this, and then I get the answer immediately. So with a computer or calculator, this provides a very fast way of solving even a very large system of equations, with the caveat that it has to be square. You have to have the same number of equations as you have unknowns in order for this to work. The other big advantage is that if you're solving lots of system of equations, like let's say you have many system of equations of the form AX equals B. In a lot of cases, the coefficients of A, like if you're collecting data from an experiment over and over again, the coefficients of A often represent how you're setting up the experiment, and the values in B often represent the results you get from the experiment. So if you're doing the same experiment over and over again, but getting slightly different results each time, if you have a lot of systems of equations where the coefficients are all the same, but the results on the other side of the equation are different for each one, solving that same system of equations over and over and over again is going to be really tedious. But if they all have the same coefficients, you can just find A inverse once using this procedure or a computer, and then multiply A inverse by any B vector to immediately get the corresponding solution for X. So this is very handy if you're solving lots of systems of equations that all have the same coefficient matrix, but just different B vectors. Find A inverse once and multiply by whatever the B vector is to immediately find the X solution for that B vector. So that's another advantage of this inverse matrix approach. Again, it only works for square matrices, and even then only if the matrix can be row reduced all the way to the identity matrix. But for those matrices, non-singular matrices, it's a very useful tool. Any other questions on that?
I have a quick question. So square matrix, is it like, it has to be like 3 by 3, not like 3 by 2? That's not a square.
Right, square in the sense that its height and its width are the same value, same number of rows as columns.
Okay, that makes sense. Thank you.
You're welcome. See you next time.
Thank you. Bye-bye.